SwayamPrabha. Digital India. Educated India.
Welcome back. Today we will be discussing few problems related to properties of pure substances. Question 1. Water initially at 300 kilopascal and 250 degrees Celsius is contained in a piston cylinder device fitted with stops. So, this is a piston cylinder device which has stops. The water is allowed to cool at constant pressure until it exists as saturated vapor and the piston rests on the stops. So, initially pressure is 300 kilopascal and temperature is 250 degrees Celsius. Then it is cooled further. When the pressure remains 300 kilopascal, this is a constant pressure process and the water becomes saturated vapor. Then the water continues to cool until the pressure is 100 kilopascal. The water is cooled when the pressure decreases to 100 kilopascal. On TV diagrams sketched with respect to the saturation lines, the process curve passing through both the initial, intermediate and final states of the water, and we have to label the T, P and V values for end state of the process curves and find the overall change in internal energy between the initial and final states per unit mass of water. So, initially water is at 300 kilopascal and 250 degrees Celsius. If we see from steam tables of saturated water at 250 degrees Celsius, the saturation pressure, this value is 3976.2 kilopascal. So, this pressure is much higher than the applied pressure, which is 300 kilopascal. It means that water at this stage is in superheated state. So, values from this, we cannot take values from this table. So, we need to look into superheated water table. In superheated water table at 250 degrees Celsius and 300 kilopascal, which is equivalent to 0.3 megapascal, the values are these. So, the value of internal energy U1 is 2728.9 kilojoule per kg. In state 2, it is mentioned in the question that water is a saturated vapor and the pressure is same as initial pressure. So, taking the properties of water from the saturated water table at a pressure of 300 kilopascal. So, it is a saturated vapor. So, the temperature at this state will be 133.52, this value. So, T2 will be 133.52, which is the saturation temperature at this pressure, and the value of specific volume is equal to Vg, which is 0.60582 meter cube per kg. Next, it is said that now the piston rest on the stops, and so it means that the volume of the piston cylinder device is not changing and pressure is now decreasing. So, pressure reduces to 100 kilopascal and the volume or specific volume is constant because mass is not changing, overall volume is not changing. So, specific volume is same as V2. So, this V3 is same as V2. From the saturated water table, if we see at 100 kilopascal, the saturation temperature is 99.61 degrees Celsius and the values of specific volume of liquid, which is 0.001043, and for vapor it is 1.6941. So, the specific volume of our system lies between Vf and Vg. It means that the system is a mixture of saturated water vapor. So, we need to calculate the quality of this mixture. So, we can write that V3, the specific volume at state 3, is equal to Vf plus X3, which is the quality, multiplied by Vg minus Vf. V3 is known, which is Vf is also known from the table, plus X3. So, Vg minus Vf is so this gives a value of X3, which is 0.3571. Now we know the quality of this saturated water vapor mixture. To calculate the internal energy, we can use similar formula for internal energy. So, U3 is equal to Uf plus X Ug minus Uf. So, putting all the values, we can calculate U3. So, the value of Uf is 417.40, X is 0.3571, Ug is 2505.6, this value, this is X3 minus 417.40. So, this gives a value of U3, which is 1163.30 kilojoule per kg. So, now we have the value of internal energy at all these states. So, the overall change in internal energy delta U, which is equal to U3 minus U1. So, U3 is, as we have calculated, 1163.30 and U1 is 2728.9. So, this is equal to minus 1565.6 kilojoule per kg. Internal energy of the system is decreasing. Now, we also had to plot TV diagram. So, if we think what we have done, this is T and V, these are the saturation lines. So, initially the system was in superheated state. So, this region here is a superheated, here this region is compressed liquid, inside this is mixture of saturated water and vapor. Initially it was superheated, so somewhere in this region it should lie, and the pressure was 300 kilopascal. So, if we draw a line corresponding to 300 kilopascal, so this point should lie at 300 kilopascal, and the temperature is also given, which is 250 degrees Celsius. So, the temperature here is 250 degrees Celsius and pressure is 300 kilopascal. Now, it is cooled and the pressure is constant. So, it should move along this line as the pressure is constant, and it becomes, in the state 2, it becomes saturated vapor. So, this is the point 2 where it becomes saturated vapor. Then again it is cooled such that the pressure reduces to 100 kilopascal. So, pressure is reducing. So, for 100 kilopascal we will have such a line. So, the pressure is reducing and to 100 kilopascal, and the volume or specific volume is constant. So, it will be a vertical line. So, this point represents the final state. So, this is the TV diagram of the entire process. Moving on to the next question, we need to complete this table for water. So, few properties are given and we need to find out the other properties with the help of steam table. In the first, The temperature is given to be 50 degrees Celsius and specific volume is given 7.72. We need to find pressure and the phase. So, if we look into saturated water table at this 50 degrees Celsius, we find that the specific volume which is given lies between Vf and Vg. It means that this is a mixture of saturated liquid vapor. So, phase is saturated liquid vapor, but we need to know the pressure. So, pressure for a saturated liquid vapor mixture is same as the saturation pressure. So, the pressure of the system will be 12.352 kilopascal. The pressure of the system is given and it is given that it is a saturated vapor. So, again looking into the saturated water pressure table at 400 kilopascal, it is a saturated vapor. So, temperature will be same as the saturation temperature. So, temperature is 143.61 degrees Celsius and volume is Vg because it is a saturated vapor. So, volume is 0.46242 meter cube per kg. In the next case, the temperature is given as 250 degrees Celsius and pressure is 500 kilopascal. So, if we look into saturated water table at 250 degrees Celsius, saturation pressure is 3976.2, P saturation is much greater than the applied pressure P, which is 500 kilopascal. It means that the water is in superheated state. So, it is superheated state. Now, to calculate the specific volume, we cannot use this table. So, we need to look into superheated water table for the calculation of specific volume. So, at a temperature of 250 degrees Celsius and a pressure of 500 kilopascal, which is same as 0.5 megapascal. So, specific volume is 0.47443. So, in this case it is in superheated state and the volume is 0.47443. In the next case, the temperature is given to be 120 degrees Celsius and pressure is given as 5000 kilopascal. In this saturated water table at 120 degrees Celsius, the saturation pressure is 198.67 kilopascal. So, this saturation pressure is less than applied pressure, which is 5000 kilopascal. It means that the water is in compressed state. So, it is compressed liquid. For calculating the specific volume, we need to look into compressed liquid table. At 120 degrees Celsius, the specific volume of the compressed liquid is 0.0010576. So, this problem gives us an idea of different phases and how to find what kind of phase exists at what properties. In the next question, we have to determine the specific volume, internal energy and enthalpy of compressed liquid water at 80 degrees Celsius and 20 megapascal using the saturated liquid approximation and compare these values to the ones obtained from the compressed liquid tables. Using saturated liquid approximation, the properties of compressed liquid can be approximated as the properties of liquid at the given temperature. At 80 degrees Celsius, from the saturated water table, we see the specific volume Vf is equal to specific volume 0.001029 meter cube per kg. The internal energy is equal to UF. So, internal energy is equal to UF, which is 334.97 here kilojoule per kg, and enthalpy is HF. So, this is the value 335.02 kilojoule per kg. We have to compare these values to the ones obtained from the compressed liquid table. From the compressed liquid table at 80 degrees Celsius, the specific volume is 0.0010199, the internal energy is 330.50 and enthalpy is 350.90. So, there is a difference in the two values, and if we compare the two values by calculating the errors, so error in specific volume is the difference in the values from the saturated water table and compressed liquid table. So, it is 0.001029. So, this is the value from the saturated water table, and this is from the compressed liquid. Dividing it by a value from the compressed liquid, so this gives a value of 0.90. So, the error is 0.90% in the specific volume. Similarly, in the internal energy, the error is difference in the value obtained using the saturated liquid approximation and that from the compressed liquid table. So, this, so multiplying it by 100, so this is equal to 1.35%. In the above expression also we need to multiply it by 100 to get the percentage. For enthalpy, the value is 350.90 minus 335.02 divided by the value from the compressed liquid table, multiplying it by 100. So, this gives an error of 4.53%. So, the two tables have slightly different values, but the error involved is low. Moving to the next question. In question 4, determine the specific volume of superheated water vapor at 15 megapascal and 350 degrees Celsius using the ideal gas equation, the generalized compressibility chart and the steam tables. Also determine the error involved in the first two cases. So, at 15 megapascal and 350 degrees Celsius, the water is in the superheated state. So, if we use the ideal gas equation, so it is P V is equal to R T. For water, R is 0.4615 kilopascal meter cube per kg Kelvin. V is equal to RT by P. So, 0.4615, temperature is 350 plus 273.15 divided by 15 megapascal or 15,000 kilopascal. So, this gives a value of 0.01917 meter cube per kg. So, this is the value of specific volume using the ideal gas equation. From the generalized compressibility chart, for that we need to have the value of compressibility factor, that is Z. For calculating that, we should know PR, that is reduced pressure and reduced temperature, and reduced pressure is P by PC, that is critical pressure, and reduced temperature is T by the critical temperature. The critical pressure is 22.06 megapascal. Critical temperature is 647.1 Kelvin. So, reduced pressure will be 15, which is the pressure, divided by critical pressure 22.06. So, this comes out to be 0.679. For reduced temperature, this is 350 plus 273.15, which is the temperature of the system, divided by the critical temperature, which is 647.1. So, this is 0.962. Now, we need to calculate the value of compressibility factor Z using this value of P reduced pressure and reduced temperature from the compressibility chart. So, in the compressibility chart, the value of PR is 0.679. So, it lies somewhere here, and the value of reduced temperature is 0.962. So, these are the different lines for different reduced temperature. So, we have to look for a value of 0.962. This is around 1.0. This is a reduced temperature of 0.91. So, a value will lie somewhere between these two, will lie somewhere like this. So, approximately the value of Z, if we see, so this is around 0.65. So, from this we get a value of Z which is close to 0.65. So, now we have Z is equal to 0.65. We can apply the equation, that is PV is equal to ZRT. So, this is also V is equal to Z multiplied by V from the ideal gas equation which we have obtained earlier. So, this value is 0.65 multiplied by 0.01917. So, the value of V is 0.01246 meter cube per kg. We also have to calculate the error involved in the two compared to the steam values from the steam table. So, if we see in the steam table at 350 degrees Celsius, the value of V is 0.011481. So, error for ideal gas is 0.01917 minus 0.011481 divided by the value from the steam table, multiplying it by 100 to get the percentage error. So, this comes out to be 66.97%. So, the percentage error is very high. Similarly, the error from the compressibility chart is 0.0. So, this is the value of specific volume obtained minus the value which is obtained from the steam table divided by the value from the steam table, multiplying this by 100. So, this comes out to be 8.5%. So, the error has reduced considerably using this compressibility chart. Moving on to the next question. In this question, a 0.3 meter cube rigid vessel initially contains saturated liquid vapor mixture of water at 150 degrees Celsius. So, volume, total volume is 0.3 meter cube and temperature is 150 degrees Celsius. It is heated until it reaches the critical state. At critical state, specific volume is equal to critical volume. This vessel is rigid and as no mass is going out or coming inside, so the total specific volume initially is also same as V2, which is same as the critical volume. The critical volume of water is 0.003106 meter cube per kg. So, we can calculate the total mass of water in the vessel. Total mass is total volume divided by specific volume. This is equal to 0.3, which is the total volume, and the specific volume is 0.003106. So, this is equal to 96.60 kg. So, total mass is 96.60 kg. The water is now heated until it reaches the critical state. We have to determine the mass of the liquid water and the volume occupied by the liquid at the initial state. We know that it is a mixture of saturated liquid vapor. So, we can calculate the quality of this mixture. So, from table of saturated water at 150 degrees Celsius, if we see the value of Vf, that is specific volume of liquid, is this, and the specific volume of vapor is this. We know the specific volume of the system. So, Vc, which is equal to V1 is equal to Vf plus x1 multiplied by Vg minus Vf. So, putting the values of Vc, Vf is 0.001091 plus x1 and Vg minus Vf. So, this gives a value of x1, so 0.005148. This is the quality of the mixture in the initial state. We have to determine the mass of the liquid water and the volume occupied by the liquid at the initial state. So, quality is mass of vapor divided by total mass. So, therefore, total mass is known, mv is equal to x1 multiplied by total mass, which is 96.60 kg. So, x1 is 0.005148 multiplying it by total mass. So, mass of vapor is equal to 0.497 kg. Mass of liquid, which is mf, is equal to total mass 6.60 minus mass of vapor. This is equal to 96.10 kg. So, now we know the mass of liquid water in the system. To calculate the volume occupied by the liquid, Vf is equal to mass of the liquid into specific volume of the liquid. So, mass of liquid is 96.10 and the specific volume of the liquid is 0.001091. So, this is equal to 0.105 meter cube. So, this is the initial volume occupied by the liquid. If we draw the TV diagram for this is G, V. So, some initially at point 1, it is a saturated liquid vapor mixture with X, which is 0.005148, and then the specific volume remains constant and it is heated such that it reaches a critical point. This is a vertical line, and from this point it reaches to stage 2, which is a critical point. So, this is critical point. So, with this we end this lecture. See you in the next lecture.